This is a joint work with Pascal Merindol and Jean-Claude Poncio from University of Strasbourg, Stefano Vesiccio from UCL in Belgium, and Pierre-François from EMD Networks at Madrid. So first, a short introduction. We're in the context of intra-domain routing protocols and running on ISP networks. So such protocols generally are link state ones, such as OSPF on ISIS, possibly running MPLS. And in these networks, there is frequent topological changes. So this talk focuses on plane changes, such as maintenance operations or traffic engineering, but it could also be extended to end-plane change, such as link or node failures. So each time we have a topological change, we would have a convergence period, during which the network could be in a transient inconsistent state because all the routers won't update at the same time. And this could cause traffic disruptions, such as transient loops. So how do these loops appear? What are these loops? Well, these loops appear because we do not know in which order the routers will update. And we can predict that one router will update before and after another one because of LSA flooding and ribbon feed computing time. So here is a small example. Initially, we consider that B and A reach destination B through link P1. But if we have a change in this network and P1 becomes less attractive than P2, then it is likely that router A will notice the change before B, will start sending data towards the destination B through B, while B still uses A. And this will cause a transient loop. This loop will cause increased latency and maybe even packet losses due to TTL exceeded and also congestion issues. And it will last until B updates. So how do we prevent such a loop? Well, actually it's quite simple in theory. We just need to force the routers to update in the right order. In the same example as before, if we consider the change on P1 or P2, but we force B to update first. So B will start sending its data to B through P2, while A still uses P1. And then A could safely update and use B because B will no longer use A. So that's the goal, but there is several approaches to reach this goal. The first one was proposed in Infocom 2005, and it was called ordered fib or OFib. It was based on explicit router update ordering with signalization messages and so on. The problem is that this solution relies on protocol extensions and is also non-incremental. All routers in the network may support this solution in order for it to be actually usable by the operator. So another solution is the IGP migration, but well, this one is very good for network-wide migration, but it has a huge overhead for a single node or a single link modification. So a third one, which was first proposed in Infocom in 2007, and is called metric increment, relies on progressive link weight update. And this does not require any protocol extension. But the problem is that this version was suited only for single link modifications. in this work, we'll extend, well, actually it's a whole different algorithm, but we will try to extend this approach to node-wide modifications. So here is the basic idea of this solution, of this approach. We want to split up the change, the modification on a link or node, into a sequence of loop-free updates, such that there is no transient loop between subsequent updates. And our challenge will be to have a sequence of minimal length, because after each intermediate increment or intermediate update, we would have to wait for the whole network to converge. So it can take a few seconds, and we would like to shorten this time as much as possible. And we also want an efficient algorithm in order for it to be embedded in router OS, even though it's not necessary. So here is an illustration of this approach. We consider this gadget and the route towards destination B. Initially, all the nodes on the left will use the red path to reach D. But if we change the weight on the link AD from 2 to 50, then the nodes on the left will use the green path instead, and the link CD. That may cause up to 3 transient loops that we could avoid with incremental updates. So first, if instead of 2, we increase the weight on link AD to 5. Only the node C will update, because the red path will be still more interesting for both B and A. Then we could do the same for node B, forcing it to reroute and use the green path, while A still uses the red one. Finally, we could do the same for node A and put 50 on this link. There will be no transient loop, at least for this destination. And as you can see, here we have intervals of possible metrics, of possible increments. So instead of 5 for the first increment, I could have used either 6 or 7. It would have had exactly the same effect. So now, let's extend it to node shut operation. What we want is to allow an operator to shut a router down without triggering any transient loop or transient program. So first, a simple solution would be to shut down each link one by one using the link shut solution described in 2007. But for example, if we need 2 intermediate increments for each link, and we have 4 outgoing links of the node, we will need 8 intermediate steps in order to remove this node. However, there is a better or smarter solution which relies on an existing OSPF and ISIS feature, allowing to simultaneously modify the weight on multiple outgoing links of a single node. So in this example, we could apply our increments on the 4 links at once and reduce the number of intermediate steps from 8 to only 2. However, these increments are much more complicated to compute because there is much more constraints to be taken into account. So let's consider this gadget. First, in order to reach destination A, all the nodes will use the red path. But if we remove node B, then they will use the green path instead. And note that the blue arrows stands for both a green and red arrow. So in this case, we would have a transient loop that could appear between router F and G. In order to prevent it, the first step will be to compute what we call the delta vector. The delta vector for a given node, in this example for node F and or G, will represent the lowest possible increment such that the associated node will start using its green path, its new path, not through the node we want to share. And this delta vector also represents the greatest value, the greatest increment, such that the associative node still uses its old path through the node we want to remove. So this delta vector is equal to the difference between the new distance towards the destination and the old one through each outgoing link of the node we want to remove. So for example, for node F, it will be equal to 5, 3, which means that if we increase the weight of link DC by 5 and the weight of link DB by 3, then node F will use both its green and red path to reach A. And note that in this example, we ignore the link DG. And we consider that it's only one direction link. So then we'll do the same for node G, which is also involved in the loop. And we will have 7, 5. And from there, we will compute the constraint associated to the loop. So in order to avoid the loop L1 between F and G, what we would want is to, in the intermediate state, is to prevent node F from using its old path, its red arrow toward G, so that we would need an intermediate increment which is strictly greater than the delta vector of node F, strictly greater than 5, 3. And we also want to prevent node G from using its green arrow toward F, its new path. So we would want an increment which is not strictly greater, which is not greater than the delta value of node G. And strictly greater does not mean, not strictly greater does not mean lower. It means lower on at least one index. And that's why we have this particular L shape. It's because of the asymmetry of the bounds. So that was for one destination, for destination A. But then we will have to consider all possible destinations, and for example, destination C. For this one, we could have two transient loops, L2 and L3, between respectively E and F and G, so that we compute the associated delta values for this destination, and we have 8, 0 for E, 12, 0 for F, and 14, 0 for G. The 0 on the second index means that there is no constraint on this index. And that's why when we modelize the constraint, it's a strip shape rather than a leg shape. So we do that for the two loops. And then we will do the same for all other destinations in the graph. And for example, we could have a constraint C4 and also C5. No, what we want is to compute an update sequence that allows to prevent all of these loops. So this sequence will have to meet each of these constraints. In order to compute it, we will use what we call the greedy backward algorithm, GBA. And it is quite simple. We start from the end, from the highest possible vector, and we try to compute the lowest vector, the lowest increment vector that does not violate a constraint. So that's in red our loop-free transition bound that we do not want to cross. So here is our first intermediate vector, which allows to prevent C3, 4, and 5, so that we can remove this constraint and we can solve the two remaining ones with only one additional vector, solving C1 and C2. So we solve this problem, this constraint problem, with two intermediate steps. And we prove that this algorithm always computes the minimal sequence of intermediate increments that prevents all possible convergence loops. Then we evaluated the performances of our algorithm on different real ISP networks, and that's what we had for the largest topology. It's a graph with more than 1,000 nodes and 4,000 links. And in this topology, we noticed that more than 90% of the nodes require at most 3 intermediate steps in order to prevent all possible convergence loops. And to conclude, with this algorithm, we have a minimal solution and the shortest possible sequences, a time-efficient algorithm with a polynomial complexity, even though I haven't enough time to present the complexity of the algorithm. And it's also a generic approach which covers the single link problem. We can use very same algorithm for a single link. And actually, for as many outgoing links of a single node as you want. So this is a practical solution which could be easily implemented either in the router itself or in a network management tool. And well, our future works will consist in implementing this algorithm in Quagga and also evaluating the performances on a real network. So on a real network, we will apply our intermediate increments during a real maintenance operation and see that there is no function loops. So thank you for your attention.
Very good. Any questions?
So I understand how you get the sequence of iterations that you want to do. Can you say what the timing is? How long do you have to keep each iteration so that it actually works? I mean, this information is probably in the name there.
It depends on the size of the network. But typically it's a few seconds. But a few seconds do not matter for a maintenance operation. It does not matter if the operator must wait for, 30 seconds before actually shutting down the link or a router.
So you would have to make the worst case assumption, you wait that long,
yeah.
And then you go to the next iteration.
Yeah.
Other questions?